Hello everyone, welcome to my video on mathematical induction part 2. So the focus of this video is going to be the second principle of mathematical induction. But before I do that, I want to give you a quick reminder of the first principle of mathematical induction. So remember, the idea is that we have this sequence of statements that we want to prove. So there's a first instance of the statement you want to prove. That's P of R. So R is your smallest integer for which this statement makes sense. And then you want to prove P of R is true, P of R plus 1, P of R plus 2, all of them, all the way down the line. So you got this infinity of statements that you want to prove are true. And of course, you can't go one by one and prove an infinity of statements. So we need a quicker way to do that, and that's where induction comes in. So induction, the first principle, says if you want to prove all of those statements are true, what you have to do is first establish the base case, which is to establish that the first statement, P of R, is true. Usually that's pretty straightforward. And then second, you want to establish the inductive step is true. So the inductive step in the first principle of mathematical induction says you need to start with an arbitrary integer k that's greater than or equal to r, and you want to prove that the truth of P of k implies the truth of P of k plus 1. So anytime one of these statements is true, then the next one is true, is what you're proving. So if you can establish those two things, then you have proven all of those statements are true. So as a reminder of how this works, let's do a quick example. So in the example that I have queued up here for us, we want to use the first principle of mathematical induction to prove that 6 divides n cubed minus n for every n in the integers that is greater than or equal to 0. So in this problem, our base case is n equals 0. So let's do it. So proof. So first we'll do the base case. All right, so we'll just point out that when n equals to 0, the statement that we want to prove is that 6 divides 0 cubed minus 0. And since we know that 0 cubed minus 0 is just 0, and 0 can be written as 6 times the integer 0, this statement is true. So that establishes the base case. And so now let's move to the inductive step. All right, so for the inductive step, we're going to take an integer k, and the integer k needs to be greater than or equal to our base case, which is 0, so let's have k be bigger than or equal to 0. And then we need to assume the kth version of the thing that we want to be true is true. So we suppose that 6 divides k cubed minus k. So this assumption that we've made here, we usually call that the inductive hypothesis. So we want to use that inductive hypothesis to prove that the next version of the statement is true. Now the next version of the statement that we want to prove is that 6 divides k plus 1 cubed minus k plus 1. And in doing that, we're going to have to look at this expression here, k plus 1 cubed minus k plus 1, and we want to argue that we can factor a 6 out of it. And we'll have to use our inductive hypothesis to make that happen. So if we flesh out what our inductive hypothesis means, that means that k cubed minus k can be expressed as 6 times some integer. So let's do that. Let's put that into our proof and take advantage of the fact that k cubed minus k can be written as 6 times an integer to get at this over here that we want to factor a 6 out of. Write out what it means to say 6 divides k cubed minus k. So thus there exists some integer L such that k cubed minus k is equal to 6 times L. So now we want to take a look at that expression, k plus 1 quantity cubed minus k plus 1. And I remember from algebra class that I could take that k plus 1 and cube it out, and there's a quick formula for that. And it works out to be k cubed plus 3k squared plus 3k plus 1. Then I still have that minus k plus 1. And so I'm looking at that algebraic expression, and I'm thinking about how I can use my inductive hypothesis. For my inductive hypothesis, I've got k cubed minus k can be written as 6 times L. So I'm looking, can I find a k cubed minus k in there somewhere? And sure enough, you see k cubed here and you see minus k here. So let's gather those two terms together so we can take advantage of our inductive hypothesis. And so that ends up giving you k cubed minus k plus, and then what's left over is 3 times k squared plus k. I had 2 terms left with the 3 on them, so I went ahead and pulled the 3 off. Okay, so I'm feeling kind of good about this, because this term right here I know I can pull a 6 out of. But I'm looking at the second part of this, I'm wondering, how the heck am I going to pull a 6 out of that? I see that I can pull a 3 out of it, but I don't see a 6. But upon a moment's reflection, if you write that as 3 times, you can factor a k out. You get 3 times k, and then you'd have k plus 1. What I'm realizing is that k times k plus 1 has to be even, because k is either even or odd, right? So if k is even, then k plus 1 is going to be odd. And if k is odd, then k plus 1 is even. So one of those two numbers there, this one or this one, has to be even. So that means the product there is even. So this is telling me that this part right here can be written as like 2 times some integer m, right? And then I've got a 3 times a 2 is a 6. So I guess I need to point that out. So let's observe that k times k plus 1 is even. So there exists some m in the integers such that k times k plus 1 is equal to 2 times m. So now we've got what we need. Our original k plus 1 cubed minus k plus 1 we see is equal to 6 times L. That's that part of the expression. And then this part over here is going to be 3 times 2m, which is 6m, plus 6m, which is 6 times L plus m. And we know that that L plus m is an integer because we knew L was an integer and we knew m was an integer. And therefore, having shown that we can pull a 6 out of the whole expression, we see that 6 divides it. So 6 divides k plus 1 cubed plus k plus 1, or minus k plus 1. And that's the proof, because we've now established the inductive step and the base case. So by the first principle of mathematical induction, we've got it. Okay, so that's how the first principle works. So now let's have a look at the second principle of mathematical induction. It's the same setup. We have some fixed integer r that's the first instance where our statement p of n makes sense. So p of n is a statement for every integer n greater than or equal to r. So that's identical to the first principle of mathematical induction. And so again, if we can establish part 1, that p of r is true, so the first instance of those statements is true, again, that's called the base case. And then part 2, now this is where it's a little different. So in the first principle of mathematical induction, we just had to show that if any one of those statements is true, then the next statement is true. But here it's a little bit more. It says that if p of m is true for every integer m starting at r and up to but strictly less than k is true, if that truth implies that the next thing, p of k, is true, then that, along with the base case, establishes that all of those statements are true. So this part of the thing sometimes throws students for a loop. But all that's going on here is that we're assuming not just that the one of those statements being true implies the next one is true. It's more like if all of the statements are true up to a point, that proves that the next one is true. Let's spell this out really clearly. So what's the difference between the first principle and the second principle? So in the inductive step of the first principle of mathematical induction, the inductive hypothesis is just that P of K is true. And then what you want to prove is that the next statement is true. So you want to prove that P of K plus 1 is true in the inductive step. But in the second principle, the inductive hypothesis is, if you spell it out sort of in a less condensed way, you're assuming that P of R is true. You're assuming that P of R plus 1, all the way up to P of K minus 1 are all true. So you're not just supposing the previous case is true, you're supposing that all of the previous cases all the way down to the base case, all of those are true. And then you prove that the next case is true. And so the next case is P of K is true. Now, it doesn't really matter if in the inductive hypothesis you wanted to go all the way up to P of K. You could do that, but then you would need to do P of K plus 1 is true. But basically the idea is you suppose that the statement is true starting at the base case and all the way up to some arbitrary point. All of those are true. Then on the basis of that hypothesis, you want to prove that the very next case is true. So the difference really is that in the second principle of mathematical induction, you have a lot more hypotheses in your inductive hypothesis. Sometimes the second principle, it gives you more to work with in your hypotheses. It makes it a little easier to prove what it is you're trying to prove. You don't always need it. So if you don't need it, you don't use it. So it's sort of this analogy of you don't use this. So you could use the second principle all the time and just dispense with the first principle. But that's sort of like swatting a fly with a sledgehammer. You don't want to take more hypotheses than are necessary. So if you can get the job done using the first principle, which only has that one hypothesis that the one previous case is true, do that. But if you realize you can't, that's not enough information, then you might try the second principle. Sometimes the second principle of mathematical induction is called strong induction. Let's see a couple of examples of how to use the second principle of mathematical induction. But the key thing to remember is it's really not that big of a difference. It's just how many hypotheses you take in the inductive hypothesis. So here's a cute example that I kind of like. So I want to prove that any amount of postage of 8 cents or more can be made using only 5 cent and 3 cent stamps. So maybe let's think about how do we turn this into a more mathematical sounding problem. Rephrasing this, basically what we want to show is that for every integer n with n greater than equal to 8, well, there's a certain number of these 5 cent stamps and there's a certain number of these 3 cent stamps. So let's give that number, those numbers, names. There exists some number of 5 cent stamps, let's call that A, and there exists some number of 3 cent stamps, let's call that B, and of course those are integer amounts. Now we can't have a negative number of stamps. I suppose we could get away with using 0 5 cent stamps sometimes, or 0 3 cent stamps. So let's specify that the A and the B are greater than or equal to 0, such that our amount of postage, which we're calling n, can be written as 3 times the number of 3 cent stamps plus 5 times the number of 5 cent stamps. So now that we have a more mathematical expression for what it is we want to prove, what we're going to do is use strong induction to prove it. What we're going to do is we're going to induct on the number n using the second principle. Okay, so starting with the base case. Well, in fact, when you do strong induction, sometimes you need to establish more than one base case. So I'm going to do a few base cases, and the reason for this will be revealed shortly when we start doing the inductive step. The base cases here, we certainly have to start with n is equal to 8, but we need to establish the truth for 9 and 10 as well. I want to establish that a postage of 8 cents, 9 cents, and 10 cents can be, we can do that in terms of 5 cent and 3 cent stamps. So, well, 8 can be written as 5 times 1 plus 3 times 1. So that, 8 cents postage can be done with 1 5-cent stamp and 1 3-cent stamp. 9, well, you can just use 3 3-cent stamps in that case, and 0 5-cent stamps. So 5 times 0 plus 3 times 0, or 3 times 3. And 10, well, you could use 2 5-cent stamps. So that'd be 5 times 2, and then 0 3-cent stamps, so 3 times 0. Okay, so next, let's do the inductive step. I'm going to assume that my arbitrary k is greater than or equal to 11, having already established the 8, 9, and 10 cases. So let k be an integer with k greater than or equal to 11. So k could be 100, whatever, but I'm just starting at greater than or equal to 11, and you'll see why I'm starting at 11 rather than 8 in a moment. So we got to suppose the inductive hypothesis. So the inductive hypothesis is we want to suppose that any amount of postage starting at 8 and all the way up to k can be expressed in terms of 5-cent stamps and 3-cent stamps. So let's suppose that for every integer m satisfying m is greater than or equal to 8 but less than k, there exist integers a and b with a and b greater than or equal to 0, such that m can be written as 3 times a plus 5 times b. So what we've effectively assumed here is we've assumed that 8 cents postage, 9 cents postage, 10 cents postage, all the way up to whatever k minus 1 is, can always be expressed in terms of 5-cent stamps and 3-cent stamps. So now we want to consider the kth case. That's the next thing in the list. We've done it all the way up to k minus 1, so now consider k. Well, k can be written as k minus 3 plus 3. And here's where it's revealed why I needed to start k at 11. So if you look at k minus 3 there, you see that k minus 3 is greater than or equal to 8, right? Because k was greater than or equal to 11, so if I subtract 3, it's going to be greater than or equal to 8. And greater than or equal to 8 is what I need. I also know that k minus 3 is less than k. So I'm going to say something like, well, notice that k minus 3 is greater than or equal to 8, but it's also certainly less than k, right? K minus 3 here satisfies this inequality, so it's an instance of one of these m's. And so any m that falls between 8 and k like this has this property that there exists an a and a b, and you can write that expression as 3 times a plus 5 times b. So by our inductive hypothesis, there exists some a and some b in the integers that are greater than, a and b are both greater than or equal to 0. And we know that k minus 3 is 3 times a plus 5 times b. Great. So now, if we go back to k is k minus 3 plus 3. And so by substitution here, we get 3 times a plus 5 times b, because that's what k minus 3 is equal to. We still have this plus 3 here. But I can write that as 3 times a plus 1 plus 5 times b. And we see that a plus 1 and b are integers, with a plus 1 and b both being greater than or equal to 0. So there I have it. I've established that k here is 3 times an integer plus 5 times an integer, where both of those integers are greater than or equal to 0. So I've expressed k as a number of 3-cent stamps plus a number of 5-cent stamps. So I've established the inductive step, and that's the proof. So the reason I needed strong induction on this problem was because of the trick I was doing in it. I wanted to do this k minus 3 trick, but k minus 3 isn't just the previous instance of k. It's not just k minus 1, right? If it was just k minus 1, I could have used just regular, the first principle of mathematical induction. But this is falling back 3 steps, and so since I needed to fall back more than one step instead of just the previous case, but a few steps back in the list of things, that's where you need strong induction. And so that's what I used. So sometimes, before you write up your formal induction proof, it's kind of a good idea to sort of in scratch work, kind of work out what the inductive step is going to look like. So if in doing your scratch work for the inductive step, you realize that it's not good enough just to use the previous instance of the statement to get the next statement. If you realize that you need to fall back a few steps, then that's where you need to use strong induction. And so you kind of want to figure that out before you start writing up your formal proof. And also this bit about needing k greater than or equal to 11, I wanted to, whatever I picked k to be, I knew I was going to have to do minus 3 from my scratch work on this, right? And so I wanted to specify k is greater than 11 so that when I look at k minus 3, I don't go below 8. I don't want to set up an expression that could possibly be less than the base case. So this reveals itself in your scratch work too. Depending on how far you need to fall back, that tells you how many base cases you need to establish so that you don't run into trouble. Let's do another sort of famous example that uses the second principle of mathematical induction. So here we're going to prove the existence part of what's called the fundamental theorem of arithmetic. So the fundamental theorem of arithmetic is pretty familiar. It just says that every integer greater than or equal to 2 can be factored uniquely as a product of powers of primes. So we're not going to prove the uniqueness part of it. We're just going to prove that you can factor it. But, there's lots, if you take any, like for example, if you take 12, you can write that as like, well, it's 3 times 4, right? So it'd be 3 to the 1 times 2 to the 2. So that's a product of powers of primes. Or if you took 48, this would be 2 to the 4th times 3 to the 1. So things like that. You can always factor an integer as a product of powers of primes. And in fact, there's a unique way you can do it, but we won't prove the uniqueness. I just want to prove that you can factor it like that. So let's do that. So since our integers that we're considering start at 2, 2 will be our base case, right? Because of the nature of how this proof works, I won't have to establish several base cases, just need to do n equals 2. Okay, well, 2 equals 2 to the 1 is trivially a product of powers of primes, since 2 itself is prime. So anytime a number is prime, it's not really a product, but I suppose you can think of just the number itself as a trivial product. Okay, now let's look at the inductive step. Okay, so we want to take k in the integers, and we want it to be greater than or equal to our base case. And now we want to make our inductive hypothesis. So we want to suppose that every integer that falls between the base case and whatever k is can be written as a product of powers of primes. So suppose that for every m in the integers satisfying, well, our m here needs to be greater than or equal to the base case, but then less than our k. I suppose if we want to make this make sense, when we set up what k is, we want to say that k is strictly greater than the base case. So we want to suppose that for every such m can be factored as a product of powers of primes. Okay, so now We know starting at 2 and everything less than k can be written as a product of powers of primes. Now we want to consider k itself. So now consider k. K is an integer, and it's greater than 2, so it's either prime or it's not, right? So k is either prime or composite. And we're trying to prove that k can be written as a product of powers of primes. Well, if k is prime, then k, just like in the base case, is trivially a product of powers of primes. So suppose k is composite. Well, what does it mean to be composite? Composite means that it's not prime. So not prime means that there are two positive integers other than 1 and the number itself, k, that divide into k. So that means that there have to exist some integers, I don't know, let's call them a and b, I guess. And we know that those integers have to be greater than or equal to 2, but we also know because they're dividing into k that they have to be less than k, because we're supposing that these numbers that divide k are not 1 or k itself, so they have to be less than k. Of course, no number greater than or equal to, or no number greater than k can divide k. So these factors of k have to be between 2 and k, strictly less than k, such that k is equal to a times b. So k is not prime, so I can factor it as a times b, where a and b fall in this interval. But this interval right here, we've made an inductive hypothesis about any integer that falls in that interval. In our inductive hypothesis, we said if a number falls in that interval, when we called it m, then it can be factored as a product of powers of primes. So a and b both can be factored as products of powers of primes. So thus, there exists some integers. Oh gosh, what should I call them? There exists some primes. Let's call them p1, p2, all the way up to some point. I don't know, let's say ps. These are all primes. And there are powers that go with those primes. And so there exists some, let's call them x1, x2, up to xs, such that a is equal to p1 to the x1 times p2 to the x2, all the way up to ps to the xs. And also, we know the same thing for b because it's in that interval, so we know there exists some, let's say, primes q1, q2, all the way up to qt primes, and some exponents to go with those, so let's say y1, y2, all the way up to yt, such that b is equal to q1 to the y1, q2 to the y2, all the way up to qt to the yt. So thus, k is equal to a times b, recall. So that would be, these products of these two big expressions. And we're done, right? Because k now has been written as a product of powers of primes. And so that's it. So the key to this proof, and why the second principle of mathematical induction worked so well on it, was the fact that when we got to the point that k can be written, k is composite, the factors have to be in the interval of numbers that are starting at the base case and strictly less than the number we're thinking about. So those two numbers are not necessarily just one less than k. So the first principle of mathematical induction doesn't make sense here because I don't really know anything about what's happening with the number that's one less than k. But I know that if I fall back some number of steps, I can find the factors of k. So anyway, that's why strong induction works there. It turns out that to prove the uniqueness part of it, which we haven't proven, you would also use the second principle of mathematical induction. So I would leave that as a challenge to you to see if you can figure out why the factorization of k that we have down here is unique. Like, why is there not some other factorization? And usually what you do when you're trying to prove uniqueness is to suppose that you have two different factorizations, and then you argue that they have to be the same. But yeah, that proof requires second principle of mathematical induction as well, as I recall. Okay, so I think that's it. I'm going to stop there. I would like to point you to one example in the textbook that you might want just to see another example of a proof by the second principle of mathematical induction. So in our textbook, let me look here at what that example reference is. Yeah, so take a look at see example 6.17, which is to prove that 24 divides 2 times 7 to the n plus 3 times 5 to the n minus 5. That's true for every n greater than or equal to 1. This is another example where it's not entirely clear when you're trying to prove that how you can use, if you're trying to prove the kth case, how do you use the k minus first case to prove that? Or if you're trying to prove the k plus first case, how do you use the kth case to argue that? But if you can fall back a couple of steps using strong induction, then it works out. So take a look at that example. All right, I'm stopping there. Talk to you again soon. Bye.